Hello everyone, I'm the presenter Hsieh from National Cheng University in Taiwan, and my advisor is Professor Chih-Lung. It's glad to have a lecture today to introduce my research, thermal image-based band monitoring system using VLP model for elderly fall prevention. This is the outline. First of all, is the introduction of our research, and second is the system implementation. Next is experiment result. The final is summary and reference. So let's start with introduction. The growing elderly population has led to increased falls in hospital and at home, often resulting in serious injuries and psychological trauma. One major cause is elderly individuals leaving their beds without assistance. Traditional prevention methods, such as more frequent walk rounds, can help reduce falls but add to nursing staff workloads. Moreover, sleeping posture are closely linked to sleep quality. To address this, several bed monitoring systems have been developed to automatically detect bed leaving motion and record sleep posture. When integrated with electronic health records, called as EHRs, this system can provide effective long-term solution for fall prevention and sleep monitoring. However, current EHRs still rely on manual data entry from caregivers, which increase the burden on staff and can lead to mistakes due to memory error, limiting the widespread adoption of EHRs in care facilities. Imaging methods are commonly used in bed monitoring systems. Lens team utilize RGB images to track movement and detect bed leaving actions. But these images are often unclear in dark environments and raise privacy concerns due to facial recognition. Cheng et al. Proposed a method that uses infrared 3D ToF technology to capture deep image and recognize bed posture. However, ToF can produce inaccurate results due to transparent objects and multi-path interference. In contrast, thermal imagery can detect human movement without privacy issues and avoid the limitation of deep images. Therefore, this study used thermal imagery as the basis for posture recognition. Next, I will introduce our systems. The system consists of three parts: acquiring thermal radiation data, data preprocessing, and text generation. We use thermal pile array to capture thermal radiation value with a resolution of 80 by 60. The device is installed on the ceiling 2.1 meters above the bed in order to capture thermal radiation data. The Raspberry Pi used to read the radiation value from each frame and store them as a two-dimensional matrix. The thermal radiation data is then converted into thermal imagery followed by data preprocessing. Finally, the thermal imagery are input into the VLP model to generate text. Preprocessing includes three steps: normalization, resize, and background remove. For normalization, we use min-max normalization to scale the value to a range of 0 to 255 to match the pixel format required by the visual encoder of the VLP model. Then we use bicubic interpolation to resize the resolution from 80 by 60 to 224 by 224, the input size of a visual encoder. To emphasize the contour of the person on the bed, background radiation is removed using the following formula. The threshold of T is 90, obtained by averaging the pixel value of 100 thermal images without a human body, is applied to filter out the background radiation. Finally, these images are input into the VLP model to generate corresponding captions. Next, we fine-tune the visual encoder. We use VIT as the visual encoder in VLP models to extract visual features from images. Because the VIT we use is pre-trained on RGB images, it requires fine-tuning for adaptation to thermal images. The fine-tuning process is shown in this figure. A NLP layer is added to the VIT to classify images into 10 posture categories. The model segment each thermal image into 14 by 14 patches, which are then flattened and projected through a trainable linear layer to generate page embeddings. A class embedding is added to represent the categorical information of the input image. Passing the transformer encoder, the class embedding is fed into the NLP layer to classify the image. We use cross-entropy loss during training to compare predicted and the actual result. Finally, we need to fine-tune the VLP model to generate required caption. Our work utilizes the VLP2 model, which incorporates a lightweight Q-former to effectively connect the VIT and the language model. Retraining the Q-former during fine-tuning the VLP2 model, thereby reduce the high computational cost. During the training process, the weight of the VIT and the language model are frozen. The training process consists of two stages. Stage 1, image and the text pair are input into the VLP2 model. The Q-former is fine-tuned on this pair to learn the relevant visual representations, which are linked to the textual information. Stage 2, the Q-former connects to the language model through a fully connected layer. This layer is trained to project the output of the Q-former into the same dimension as the language model's text embeddings. The outputs of layer serve as a visual prompt for language model, help it to generate captions. After the system and the method, let's see the result. Our training dataset includes 770 images from 10 healthy young participants, averaging 24.1 years of age. We categorize 6 types of lying posture, 2 types of bed leaving motion, and 2 types of posture outside the bed. Totally have 10 categories. Each participant maintains the same posture on the bed for 10 seconds to simulate residual heat produced while lying down before starting the action of leaving the bed. The dataset is divided into training, validation, and the test set into an 8:1:1 ratio. As shown in the confusion matrix, the fine-tuned VIT achieves an impressive accuracy of 98.7% in identifying all thermal images. For the 6 lying posture, the fine-tuned VIT can identify all of them, achieving a recognition accuracy of 100%. Furthermore, the VIT achieves an accuracy of 96.5% in identifying thermal imagery of posture during bed leaving motion. We infer that this classification error arises from the lack of clear difference between the Hsieh and the C posture, like this figure. This result of the classification shows that the fine-tuned VIT effectively extracts visual representation of posture, helping the language model in generating accurate textual caption based on various human posture in thermal images. To evaluate the model's ability to generate caption describing human posture, all thermal images from the original dataset are fed into Believe2 model. The postures are categorized into dangerous posture, easy and fall, and other safe posture. The output caption is regarded as correct if it contains the keywords corresponding to the category of the input thermal image. Table 1 shows the keywords given to each category. Table 2 details the accuracy, position, recall, and F1 score of the caption generated by Believe2 model for each category. The results show that the Believe2 model achieves perfect score across all metrics for different postures. This shows the model's reliability in automatically recording bedside motion related to falls. These are examples of model's output. The left and the middle figure show the caption generated by Believe2 model before and after fine-tuning for the same image and question. The model accurately recognized the same posture and generated the correct caption after fine-tuning. The right figure shows the Believe2 model can detect the fall event and produce corresponding caption. This result verifies the functionality of the Believe2 model in accurately describing thermal images and generating caption for EHRs. Final is my summary. In my research, there are 4 key points I'd like to share. First of all, a bad monitoring system has proposed using the Believe2 model for posture recognition and automatic EHR captioning. Second, thermal pile array captures thermal radiation values, which are converted into thermal imagery for the Believe2 model, effectively avoiding privacy issues and challenges in dark environment. Next, the fine-tuned VIT accurately extract visual features from thermal images, helping the Believe2 model in posture recognition. Finally, the system achieves 100% accuracy in generating caption from all thermal images, confirming the feasibility of using this approach for EHR generations. These are my references. This concludes my presentation. Thank you for your attention.